You mean this one?
This one.
Yeah, for example, this actually, let's see, if we consider F equal R minus 2M R, right? In this case, G R equal R. Because this is R, this is in R, so this is actually R. You just
But this is a Schwarzschild is very simple matrix. In that case, we are taking out another matrix, except Schwarzschild and not this time.
Yeah.
Not this time.
You see?
So suppose we are taking this matrix. Minus 1 minus 2m upon square root g square plus r square.
Yeah.
Then what is the value of this?
Okay, that's a good question. Let's see, this actually you can see my F equal 1 minus 2m square r square.
G square plus r square.
Okay, r square plus a square, right? So you can see now I have actually square r square plus a square minus 2m square r square plus a square, right? This will equal r squared plus a squared minus 4m squared r squared plus a squared r squared plus a squared plus 2m. Correct? So I have this one. So now depends on if this actually has 0 or not. Suppose, let's say, we do have actually a squared, for m greater than a squared. Minus r plus r minus r minus r squared plus a squared r squared plus a squared plus 2m, correct? So this is r plus minus equal square plus minus 4m squared minus a squared, right? Suppose it is positive. But this one can simply write this right? Because it's a negative. So then you can see I have only one singularity, correct? This is my singularity because this is always positive. So then this is going to be equal to r minus plus gr, correct? So I can write this gr. Then you can extend actually Professor Sushant's solution. There's only one r, right? So if this is the case, this has to be real. If a 4m squared is greater than that, basically. Right? Then you have Brahma solution. Yeah. Because yes, remember, Professor Sushant tells us singularity only on one r equals 0. There are no other singularities, if I remember correctly. Then this is going to be correct. Okay? Good question. Any other question? Okay. You see, many things you can you do not need to, for example, I use Terra expansion. The extension does not need to integrate this correctly, express it. Remember, for the Schwarzschild solution, this is equal R. That's needed to integrate. But what about for this actually? So this solution you cannot integrate, but the extension can be done similar like this. I'm talking about your solution. So he asked a very good question. Okay. This will be easy to write out like this one. Yeah. Then you can extend this. Okay. Yeah. Any other question? Okay. So today actually we're going to This is like a black hole physics. Now you see, black hole physics is connected with gravitational waves. So that's why I think I spent talking with Professor Sushant black hole. I spent more time on introducing them. Let's work on the last 3 classes will be gravitational waves. So the gravitational waves in the weak field regime is not so complicated. So the idea is the following. We have, let's say, let me first arrive to the title now. Lecture 9. Linearized equation. So our ideas is the following. We have actually Minkowski space. That's Z, X, Y, then we just have time T. This is actually the measure of GAB. So I sometimes use GAB, so this is Minkowski. Then we, right? But now, we consider the following. We consider like when we consider quantum field theory. Not necessarily quantum field, classical field theory, moving on the background of Minkowski. So this actually now we, in certain sense, we're treating like a matter field. But this matter field always a potential, HAB.
Battery.
Yeah. Okay?
Battery. I think battery is the
Better, you know?
Yeah,
So, so the idea is now we consider this as a field. Our background is Minkowski, like actually what I normally would consider. We have a scalar field moving in the Minkowski background, right? So that's why you will see when we write along the index, we use this guy. So I want you actually understand why we do this. Actually, physically, we take this our background, then consider the measure perturbation. This should be the part of a curve. But then now we treat this like a field moving in the background, right? So this actually, the way actually, in that sense, we consider the weak field regime is a AB plus, I always introduce epsilon. So this actually gives us mark. Whenever you get an epsilon squared, first away. So when you do calculation, I suggest you put this back. Because most of the times it's very easy. If I make modification, I can simply actually loss some terms. But whenever I meet epsilon squared, I just drop. If I have epsilon, I use the kit. It's called linearized. Linearized in terms of epsilon. Okay? So epsilon, we suppose epsilon is very small quantity. Actually, HAB is, this actually we call order 1. Right? So 1. So later you can see we just observe a epsilon into HAB, so it's simply HAB. Here, this guy is small. So this is the measurement we can always do. Okay? So now I just actually use this guy like my bookmark. Any question about this problem?
Wait for 1 minute.
Okay, good.
Because voice,
Okay.
it will not pick up.
Thanks to the parents diagram. Any question? Any problem? The same thing, for example, if we consider F equal, let's say, 1 minus 2m r plus e squared r squared. Then you get extra r minus r plus r minus r minus extra r squared, right? So r minus plus equal m plus minus square root m squared minus e squared. Of course, we consider only m squared greater or equal e squared. So when m squared greater than e squared, I have two real roots. If I consider this one, this will be my g equal r minus.
Much way.
Second, So in this case, actually, this if you consider this one, this is my g. If I consider this one, this will be r minus r plus, right? So this actually, in this case, you can. I'm not so sure if you can express. Yeah, this is very you still can integrate, express it, but not. It's not necessary integrate. It's just simple expand, and expand this I know r equal r plus. This universe is not zero, right? So this is certified all my conditions. Okay, so now come back to this program. This is GAB. Now you can see what's happening. For example, I have let's say we have a GAB, GAC equal delta CB. This is our definition. This is inverse, right? So if I know this guy GAB equal eta AB plus epsilon HAB plus this is similar here. Now I want to HAB plus then multiply, so GAB. So GAB actually, what I do, definitely, this is my zero term, right? So if epsilon equals 0, this must be this one. So I have something, let's say, I wanted to put HAB, HAC, this is epsilon plus, I need to determine what's this capital HAB, right? So then you can actually AB into AC plus epsilon into AB HAC, then second order, first order. Then plus this guy's epsilon HAB eta AC. Then this one multiplies this one second order. This one multiplies the third order, high order, which is put it here. So this actually will equal my delta CB plus epsilon. You see now here A, like what I said, I simply call this will be A, B, C plus epsilon H. Here actually I take it up, the CB plus O epsilon square is equal to delta C, BC, right? Kind of. So this actually equals, so my HCB equal HCB, right? Oh, sorry, reminder. Now, one thing to remember, I'm using this actual word H BC equal eta AB HAC HCB equal eta AC HCB. So I'm writing rising index use my eta AB. Why, like what I said, now I'm considering my matrix because HAB simply are filled, moving in the Minkowski background. So when I rise or low index, I use eta AB, correct? So then you can say, okay, now this is equal minus, so I get the following. GAB, so they equal eta AB minus epsilon HAB plus where HAB equal eta AC HCB HAB equal eta BC HAC, right? So this is small. So this is actually my definition. So let's call this equation 2. Okay, once again, I'm considering this is my space-time. This guy is like a matter field moving back on my Minkowski background. So that's why I'm rising index always use eta AB, right? So this is actually one thing that easy to get a confused point. But if you consider this as a field propagating on a Minkowski background, that's fine. Okay, any question on this part? So this looks simple. When you do real calculation, I think now you have computer does this automatically. If you do by hand, always put this part there. Until the final, you see, whenever I get a second one, I drop something. Otherwise, it's very easy to miss time linear terms. Any question on this part? So this is actually our convention. We actually use, we just simply use the result, Newtonian limit. Newtonian limit here, we have actually two conditions. GAB equal eta AB plus epsilon HAB. This is also second order. But the second actually condition is the solar moving, right? So this actually V over C. The mass less than 1, mathematically, is equivalent for any given function f, dx0. This is actually all epsilon df, the spectral part. Alpha, where alpha equal 1, 2, 3, my x0 equals ct, right? So this is actually the Newtonian limit. Linearized field equation, we do not consider this condition. Why? For one, we consider gravitational waves, right? Gravitational waves take exactly V equals C. So, was a weak. So we consider gravitational was a weak. Now, I have been emphasized, people were asking the question. If you consider gravitational wave weak, now you also told me you are using gravitational waves to test GR in the strong field regime, right? Why you do this? This is a contradiction, okay? But the problem is like what I said, the gravitational wave theory is very clean. If they come from long distance to us, almost no interaction actually with others. Then it just simply start from the source time or reach us, the only change is the amplitude. Because our universe expands, right? The amplitude. The amplitude change, the waveform all keeps all the information we want in the strong field regime. That's why we see although gravitational waves are weak, we observe weak, they're so weak. still give us all the information when it was just formed, emitted. So we are studying strong gravitational field phenomena. Yeah.
Where we considering only the linear term. Will not there be non-linear terms also?
We were here in this sector, we were not. This first, we still have 3 classes. The last one I will talk about exactly non-linear term. Yeah. This is actually the linear part. Actually, why is the linear part important? What we observe, the gravitational waves, you can easily use this. But later, for example, if our equipment is, the accuracy is high enough, allow me to study, definitely we will have lots of gravitational waves. They just collide. This is a positive charge. But there is a nonlinear interaction like this. Each gravitational wave has energy. Energy equals mass. Mass and mass has a Newtonian attractive forces, right? So you can think of this way. It's actually really a nonlinear interaction. But that's actually hard. So the last lecture, I'm going to talk about this. Okay? Yeah, good. Any other question? So we will not use this one, we just simply use this one. This is called linear. Now I think we are ready. Once this is actually clear, you just simply use our actually routine. First calculate gamma A, B, C, then calculate R, A, B, C, D, then basically R, A, B, then T, A, B. Once I get this one, I know this is actually T, A, B. This is my Einstein equation. I put it here, try to find, this is Sushant. For example, this is the guys can be 2 binary black holes or embodied programmers. So now we can connect the gravitational wave with the substrate, right? So then actually we get a linear gravitational wave and hollow star, right? So this is actually our strategy to do this. Any question about this part? Once again, I think when some programs are complicated mathematically, first say, okay, what's the steps we're going to do? Then we do step by step. Once you divide the program into several steps, you will say, okay, see, nothing has to come. Just need to be patient. Okay? So now you can say, okay, then we have this section GAB, the partial derivative will be equal epsilon H A B C plus second order, right? So then, if I consider gamma A, B, C equal 1/2 G A D, so G. So this actually is simply represent D by B by D, then put a B behind this part of the derivative, the same thing you just do for C. But the last term will not change, then put a D. This actually is a pretty simple sentence, okay? So there's a rule that you can usually remember this. So if you do not remember, no problem, just go to your as textbook, use this. So then I'm going to write this 1/2 eta AD minus epsilon HAD plus. So this is actually my GABR. Then this guy is like, so you see here epsilon already out. So I'm going to simply put epsilon here. This word HDCB plus HBDC minus HDCD plus. Now, if I take epsilon 1, epsilon off of the second first order, right? You see now, this guy is multiplied that much. I have 1/2 epsilon AD epsilon h dCB plus h b dC minus h b c d plus. Where's simple? See, this guy is multiply this one's first row. This one multiply the second row. This one multiply this one multiply the third row. Then just simple this row. So I just simply get this one. This is a constant. This is the gravitational field, right? This is like our gamma A, B, C. And the next step you can calculate the Riemann tensor, right? Riemann tensor B, C, D. And there is also rules. You put actually B, D here, B, D here, this gamma C. Those. Then minus A, now the B, C, D. Okay? So this, then you have another term that's called gamma A. Now I have E here, the same thing, B, D, A, E. So this A, oh, sorry. This E, this should be A, E, E, C, around. This A, this A, E. So another term minus gamma E, B, C, gamma A, D, E. So here the E, you could, if you want, you can put it here. There's actually regular, so you can actually remember. You don't like what I said, remember this. I remember this because every day I work with this. So this actually is the E, A here, BD. This is BD, right? C here. Then this is actually BC, D here. So this is actually one-to-one transform. This guy is actually, this, we have this one, right? This one, H of them is order E. This one is order E. So this actually will be an absolute square, right? This is the same thing. So this guy, you can simply throw them away because they are order 2, right? So then you can plug this, there you get a 1 epsilon. So our not right here is a simple plug this into this expression on 2 terms, right? So once we get this, you can actually easily calculate, for example, I put A equal B, this actually my B, D equal R, A, B, A, D. By definition, then you get actually. I'm going to write this one because this one is simple. So this will give us 1 over epsilon H C A B C plus H C B A C minus both H A B minus H A B plus. So this actual equation, let's call it equal to 4, where H equal eta AB H AB and 4 equal eta AB DA DB or equal DA DA. So this actually is the definition for the mucosal you already know. If I use TX or YZ, there's a down barrel actually operator. It's hyperbolical operator. So remember in Newtonian theory, this mathematical called elliptical equation. Elliptical equation never give us waves. So Newtonian theory does not predict gravitational waves. So if we observe gravitational waves, Newtonian theory definitely cannot predict. Or Einstein theory or other theories. So what you will see, we have something later where I have these guys, A, B, closing from substitute to there's letter over the right. So this actually what? This is a wave equation, right? So Einstein theory, my theory, was different from Newtonian theory because I predicted the existence of earthquake. This is what he found 1 year after his GIAN. He proposed GIAN in 1915. In 1916, he got the waves. Yeah.
This energy momentum tensor?
Yeah, this energy momentum which produces gravitational waves.
So is it at the source point or at the field point?
This is source term. Yeah, I'm going to divide that question in this part. Just want to a side remark. Einstein's theory, Newtonian theory is an elliptical equation which does not give waves. Maxwell equation gives waves because we have this operator. Einstein's theory gives waves because we have this operator. Okay, so this is actually my side. Okay, good. Any questions? This is actually you get a Riemann tensor, then you just go next step to calculate R or whatever. So you can G, A, B, R, A, B, right? And this is already first order. So in this cycle, by definition, equal eta AB minus epsilon HAB plus O, then multiply RAB. But what I said, this cycle already first order. So this is either AB, R, AB. Then why this guy to multiply this one is had second order. This of course one is third order. So we just throw it, right? You see, linearized equation is simple. So I'm getting around here this word epsilon H CD minus box H. H actually is the truth. So this, all I have, R equals this one is my 5 equals. I have RAB, R, you can get that instantaneous, right? So this is very simple. The GAB equal RAB minus 1/2 GAB R. So this is the first order, right? So I have RAB, but this is also first order here. So this has to be 0. So equal minus eta AB R plus. So that's why it's important. I always keep this. Reminding me, I do not consider second order. This is first order, this is first order, multiply 0, first order. Okay? So perhaps I will write this explicitly because I need to write an Einstein equation. So H C A B C plus H C B A C minus box H A B. CD minus eta AB both H prime. Okay, so we have like finally got the Einstein tensor in terms of H. What I did, I suggest you always do this. Because when I was doing PhD, my supervisor had a third grade student. I arrived later. First two was almost finished. So one of his grade students was doing exactly perturbation, but more complex. Not only this perturbation in the Schwarzschild. That's very complex. So here you see the EAB. Schwarzschild background, you already know Schwarzschild solution. So exactly, she got some result totally contradictory with what we already know. So my supervisor was so busy, he said, please check her result. Because that time I just finished my PhD, writing my PhD. Then I found some term missing, actually. It's exactly here. So I just reported to my supervisor, oh, that's disaster. Because she has been working for many years. Exactly from the very beginning. So that's why you get a contradictory result. You're supposed to get something we already know in textbook. So she was a teacher, fortunately. She had a job. Finally, she didn't get her PhD because of this. So that's why I want you guys to be careful. Especially when you do numerical calculation by hand. Now use the computer, GR times automatically take care of this, so you do not need. But sometimes you need to do by hand. Just get the general structure of the equation. Computer always does not always solve your problem. If you know how to do this, for a problem like this, you need to take a really work hard first by hand. You know the structure, then you instruct the computer to do this step by step. Otherwise, I don't think you can ask your map to give you a result. No, you'll never get it.
Never get it.
Yeah. Any other question? Okay. Now you see, this is complicated, right? So I'm going to introduce another quantity which can simplify the expression. This actually, the rest is a technical problem. This actually, everything is done. So we just derive step by step.
You can even do second order perturbation.
Yeah, we can do the second order
Perturbation.
parameters. But the gauge, I'm going to talk about the gauge fixing problem.
Yeah.
That's actually, even in cosmology, right? So you can do actually, our impression, you can do actually as many orders as you can.
Even black hole perturbation.
Yeah, even black holes.
Yeah.
This actually, the gauge transformation, once you do that, you have to be careful. This actually, another, I'm going to first simplify this Jamia Millia expression. Then actually, we're going to consider gauge transformations. So I will write this GAB here. So I just simply introduce another quantity I call psi AB. Psi AB, this by definition equal HAB minus 1/2 eta AB. H. So this let's call equation 6. Oh, this is 7. Then you rewrite this. The reason why I use this one because this expression becomes simple. So then in terms of this, then you will get GAB equal 1/2 epsilon psi C A B C plus psi C B A C minus both psi A B minus eta A B psi C D C CD. Plus. So this is actually my expression. You see that instead of how many terms now, I have 1, 2, 3, 4 terms, simple. So this is actually totally equal. Now I'm going to consider the following. Remember, we are choosing Minkowski space, right? Minkowski space. So I'm going to do this one. X, let's see, Z, X, Y, 0, T. So what's happening if I choose another current? Let's see, I'm choosing X. Let's see which kind of current. I choose, let's see, something like this. This is Y prime, Z prime, X. Because I actually general currents, I'm allowed to do this, right? So if I do this, let's say this called prime current is in general equal A plus epsilon psi A plus over 2. Right? I also write this. If I do this kind of current transformations, this is called like current transformation, right? I'm choosing, you can work on this, I can work, you can work on this. This guys will be very small because I want to, we are all in a Minkowski spectrum, right? So this is actually eta AB prime or eta AB. So we are actually all in a Minkowski spectrum. This is actually like initial parameter. It's not necessarily initial parameter because this can be n. Okay? So if they are connected with this one, then you can see my GAB prime will give me DXC, DX prime A, DXD, DX prime B, GCD, right? This is actually, because this tangent, I use the color transmission. This actually here, you can see now I'm going to write this X A equal X prime A minus epsilon psi A. Now this actually is going to be function of X, right? Now X equal X prime minus epsilon psi. You can just plus O X squared over actually. This, I'm going to expand this one. X prime A minus epsilon psi A, X prime. This is the first, I'm expanding in terms of epsilon. 0 give me, then plus, right? This guy that will give me second order. You see? I simply put it here because this guy is function of X. Right? So now I want to replace X by X prime equal X, sorry, this X should be X prime minus this. So the linear is the same. Just simply replace X by X prime, here minus. Why? Because I need this one. You see, then you can dx A, dx prime B. This gives me delta AB minus epsilon say B. Correct? So once I know this one, I get a G prime AB equal dxc dx prime A dx D dx prime B G A GCD, right? CD. This could give me delta CA minus epsilon psi CA plus this is actually the first term. Now I need to multiply delta dB minus epsilon psi dB plus O epsilon squared. Then this guy, GAB eta CD plus epsilon H A CD plus O epsilon squared. Correct? So this actually you can see this multiply this one, delta C, oh, C, right? C, please help me, this part, this is the one, now minus this epsilon delta C, A, epsilon D, B, this is the, now plus, this first order is 0, so okay. So I'm beginning to actually one this now this guy's multiply this one minus epsilon delta D B say CA this multiplied second order third order. So this actually everything becomes so this actually the first part, right? So now multiply my eta CD plus epsilon H CD plus O epsilon squared. So we need, you have to replace it. This one multiply this one. This actually C equal A, D equal B. So when I multiply this, I just simply either A, B, right? This multiply. This multiply this one plus C equal A, H A, D equal B, plus epsilon H A B. This actually we will finish the second order. Now this guy's multiply this one. Minus epsilon H C D delta C A D B. So this term multiply this one. This is multiply second order and higher order. Then this one. Then minus epsilon H C D delta D B say C A plus all of them are higher order. Right? So please try to follow me because this actually the gauge issue is important. If you do not deal with the gauge transformations, you can artificially consider there's nothing, no gravitational wave, but just because of color transformation, you get a gravitational wave. That's not a real gravitational wave. Okay? So this actually equal eta AB. You see here I have a plus epsilon H AB. Now let's see what's this one. CD actually, this actually delta A, this means eta AD, right? Eta AD is a constant, I can put it here. Put it here, I can lower the D. So this becomes minus epsilon psi A comma B. Correct? This term? So this actually will give me minus psi A B. So this is a term. What about here? Here I actually D. So this will be eta C B because D equal B. Eta, this actually becomes eta C B. Then I will lower C to B, right? Because the partial derivative is constant. So this actually becomes psi B comma A. So it's a minus you can imagine because this actually equal my GAB. For GAB, you might, when I measure my GAB, I know this actually will eta AB, H prime, H AB prime prime. Right? So you do something, I do actually X prime coordinates, this is a corner transformation, right? So corner transformation is equal. This is the first order, this is the first order. So my HAB prime has to equal this. O H prime AB equal HAB minus say AB. So normally I just simply use, this is going to be A, let's call it circle. So my this address is the measurement. Okay? What does this tell us? The following. Even, for example, I do not have gravitational waves, which means this guy can be 0. In your coordinate, let's say you measure HIB equals 0, no gravitational waves. But because there are coordinate terms between us, I can measure my H prime AB is not a 0 because there are differences. But this, I cannot consider a gravitational wave, right? Because you didn't measure, if I say I measure, what's the gravitational wave? No, because it's simply the corner we use different. Like you already learned, let's say electromagnetic, we have Lorentz, the gain further. So there, if you use for potentials, A mu. So my A prime mu equal your A mu minus the partial derivative of lambda. Lambda is the function. This like two guys describe the same electromagnetic field, right? So this is the for potential. In terms of E and B, this gives the same E and B both of them, right? The same thing here. So you needed to take, so for example, you measure this quantity, I measure this quantity, we have to consider the gain. So they are called Lorentz gain, right? So we need to fix this guy. Only fix this guy, then we can say, okay, we can talk about when you measure here, let's say I measure this weight, the 0.1 kelvin. I'm going to try to measure this to be 0.1 kelvin. We need to take this difference, location difference, current difference, right? Why? Because our theory, Einstein's theory said, okay, you have this gear further. So they will have the same physical interpretation like here. My maximum equation has this gear further. You needed to take this electron freedom away into account, then you can get a consistent result. So what we did here is fix this. The same thing here. We are going to fix the gate. Once we fix the gate, we're talking about the same quantity. So that's actually the idea. So gate choice, when you do measurement, gate choice always the first question you need. Otherwise, you get a completely different result, right? Any question on this part? So now this function I have in 4 components, a vector, right? Eta 0, 1, 2, 3, 4. Oh, sorry, 1, 2, 3, 4 actual functions. I'm going to use this actual gauge further to fix this guy. What I'm going to do actually, let's say for we did other calculations in this corners, I'm going to make a corner transformation fixed gauge here. Our requires So remember this has semi-index, so this one is sum, I just simplified this. So we will choose this one so that it equals 0. Since h prime a b equal h a b minus 2 psi a b, we find h prime a b equal phi a b minus 2 times a b plus epsilon a b. This one. So this equals phi prime a b a equals 0 means phi a b a minus box so b equals 0. Or I can write the following. I want to explain what's happening. So we remember we calculate the product which is the useless GAD, eta AB plus epsilon H AB plus the second right? So now I get it as 5. So I'm working everything like I'm actually in the a mu. But I will make a corner transformation into x prime so that this function, this is a 4 arbitrary function, right? But now I'm going to choose this 4 arbitrary function. So the box of this guy equals 1, right? So this is the h mu mu we calculate in x, in t, x, y, z. Now I'm going to make corner transformation to fix my gate. Because that gate choice, I have 4 arbitrary functions, right? So I will choose my 4 arbitrary functions so that this guy is equal to 0. When I do this, actually, I have this equal 0 in my x prime coordinate, right? So please try to follow me here. So what I did is the following. You see here, because Maxwell equations, if I actually, in order to fix the gauge, I can properly choose this lambda phi, right? Normally you can also equal this 0. This is called Lorentz gauge, right? You see here I have something similar, but this equal this guy. Not 0. You give me, I can feel I solve this a Dunbar equation with sources. You can use extra mathematical this opposite. For proper choice, this one is always a solution. The main idea is we have 4 arbitrary functions. Say b standard 0, 1, 2, 3. So I'm going to choose these 4 arbitrary functions so that this satisfies this equation. You give me HAB, I can control this one, then solve this equation, plug there, I get this again. Right? So this is exactly like what we did in Lorentz, from dynamics. Okay? So once we do this, you can see, if we do this, then our equation in x prime, then we find G prime AB equal kappa T AB prime. I'm going to show you an experiment current, huh? So this actually simply becomes 1/2 epsilon box prime A prime A B equal minus cup T prime. It's so beautiful, right? Box. It's quantity H5. If I get this one, I can easily get my H, right? So this is my source term. But remember, you are working in my current. My current means actually, I made a current determination this certified. So in that current, with this gauge, this is a gauge. Because I choose this one, I get this. So if I summarize everything here, I choose x, a equals c, t, x, y, z, then I get GAB equal cover PAB. I calculate this one. So now, using this section, this is my first step. The second step, I'm going to make this corner transformation equal x, a plus epsilon c, a plus O epsilon squares, where my c a equal phi b a b. Once I do this, my actual phi prime a b a equal 0, right? Then my g prime a b, the Einstein equation in this prime coordinate, take very simple form. I work for the here. So this is my step. I linearize the Einstein equation, the kiss GAB equal eta AB plus epsilon HAB plus the second order, which I throw away. I linearize the Einstein equations. Now, I'm going to make a cardinal transformation with this set. But the set, in principle, the arbitrary function for them. I will choose this arbitrary function set so that to certify this one. This is the one I calculate here. Right? So if I choose this set so that then you can prove this guy is in the new coordinates equals 0. Once this equals 0, I can simplify my G prime AB. Then the Einstein equation takes this so simple form. Right? So this is called linearized equation with the gauge chart here. Any question on this part? Yeah? Any question? Yeah.
I'm actually confused about the energy momentum tensor as the source point and the field point.
Yeah.
Because what we are doing, as I understand, is we are seeing the scenario at the field point, right? Because
Yeah.
we are taking a perturbation
Yeah.
on the foreground of a flat space-time.
Uh-huh.
Because I'm much farther away from the source, right?
Here actually we have not assumed this yet. I just simply make a linear perturbation. I can do actually any place, but I can even say I'm actually together with my binary.
Yes.
So later I'm going to consider, okay, the source is far from us. So we observe the sources, then in our place, the binary black hole not with us. In that case, this guy equals 0. I have free Gaussian waves.
Exactly.
Yeah. but I can always connect my Fourier with a sources, use the integration. Okay? Yeah, we'll talk about this later. So the first one is we just linearize the Einstein equation. From here, they use corner term to get further. You can see that we call corner term is in terms of field surface called gate further. This gate further instead of field, I mean here the corner, right? So the same, in same sense. But here actually I will choose this for like Lorentz gate. You can choose difference. This is actually called Einstein gate, sometimes called Lorentz gate. So there are several different names. Even this is called Newtonian gate. Newtonian gate, Lorentz gate, Einstein gate, all refer to the same. Different textbooks are. So if I choose this four functions so that this one then in the experiment code this is equal to 0. Why I choose this one? This is because 0 is simplify my equation. I can easily solve the equation. It's analysis, you can say number operator in resources, I can put it. Right? Any question? Yeah.
So the problem that arises in the HAB is that coordinate transformations gave an extra term.
Yeah.
Because of which even if there is HAB is actually 0,
Uh-huh.
you can have in the new coordinate system
Yeah.
something illusion of gravitational waves.
Yeah.
So then we needed to fix the gauge.
Uh-huh.
So we fixed the gauge. So how does now, after fixing the gauge, how does now, if I do a coordinate transformation, how does this fix the problem that there will be no artificial
Yeah.
gravitational wave?
Very good. Once you fix the gate, like let's think about the Lorentz case. Once I fix the gate, the field I measure this H prime AB. This is real gravitational waves.
Okay.
Because I cannot move anymore. I just fix myself.
Yeah.
Just take the corner transformation away.
Uh-huh.
The reason because you have the full for function, right? Now, if I fix the full for function completely, suppose, then you have no more choice.
The gauge condition that you are imposing, it is on HAB actually.
Yeah.
HAB. That so yeah. Once we fix the condition on HAB, and in that particular coordinate system in which we were previously working, right?
Yeah.
So now are you saying that we cannot do a coordinate transformation anymore?
You can do, but if you force yourself to do this, you do not have, your opponent has no physical meaning.
Okay, that means, yeah, the thing is, now if I do the code, after fixing the gauge, if I do that coordinate transformation,
Yeah.
this gauge condition will not be satisfied.
No, because you already did, yeah.
And that will mean that it is artificial. Is that somehow?
That means the HAB, after you do this, there makes two parts.
Yeah.
There is due to artificial corner, there is also part due to the vertical in the way.
Yes.
So you need to separate them.
Yes.
So how you separate them? So physically, I just fix again. Once I'm actually in X prime coordinates, I know that H prime AB is due to purely gravitational wave.
Okay.
Normal, because I already take the gate freedom away, like in Lorentz gate, right?
I didn't really get it completely.
Yeah. So let's come to the Lorentz gate.
Since basically we have fixed the gauge on HAB,
Uh-huh.
first part is done. After fixing the gauge on HAB, we do the coordinate transformation.
Yeah.
So if we do the coordinate transformation, we will get a new tensor HAB prime.
Yeah.
Now my question basically is now why this new HAB prime after we have fixed the gauge does not give us the illusion of artificial wave?
Because you have four free parameters in your X, well, is in P, this set. But in my coordinates, this guy has been completely fixed.
Okay.
I do not have. I already take this freedom away.
Means when you are saying that you have taken the freedom away,
Yeah, take freedom away.
means, what does that mean? Means basically in the HAB prime,
In HAB prime, I do not have the gauge part. I have only pure, my H prime AB is pure due to the gravitational field.
okay.
Normal gauge, because normally in your X, Y, Z, T, there's two parts when you measure HAB.
Yeah.
Due to the corner choice and the real gravitational field.
So after taking that gauge, the H prime AB will not have that coordinate part.
Yeah, normal,
Only
complete.
the gravitational wave part.
Yeah, only gravitational wave part are left.
Okay. Okay.
So normally you have two parts.
Okay.
Due to the gate, due to the real gravitational field.
Yeah.
So now in my H prime, I take the artificial part away. I have pure gravitational wave.
Mm-hmm.
Then I can talk about gravitational wave.
Okay. Suppose we have taken the gauge choice that the box HAB is 0, and so we have taken it.
Yeah.
Then now someone does the coordinate transformation, so the effect has gone. The effect of the gauge has gone.
Yeah.
So that H prime AB, it must also satisfy that box H prime AB is equal to 0, right?
Yeah, this I'm getting now.
That is the point.
Yeah, this
Yeah.
I just say probably this accurate gauge choice.
Yeah.
Now the problem is a complete fixed gauge.
Huh?
I'm going to show you now.
Okay.
We still have gauge residues.
Okay.
So you need to go to the step of the corner to 100% fixed. Then you say, okay, I take the corner transformation effect 100% away. Pure gravitational wave. So now we are actually, when I do this is actually my next very good question. So this is my next step. This has not completely fixed the gauge. Why? I'm going to show you.
Okay.
We still have gauge residue. So until which step we completely fix, this is actually what I'm going to talk about. Why? I'm going to show why this not completely fix the gauge. So until you actually completely fix the gauge, then that H, let's say double prime AB, that's really 100% due to gravitational field. You see, I just take it off of my way. So this step only take part of it.
Okay.
We need to first. Yeah. Okay. So let's work out this one. This is still gauge ready. Now in X prime coordinates and with this gauge, I'm going to make another transformation. I'm going to X double prime. I will show you my phi double prime also equal to 0, which means it also Lorentz gauge, right? But I still have something like it. Something like that one, not this form. It's exactly the wave equation. Only by then, when I go to further, I completely fix my gauge. I have normal gauge for it. Then my really physical quantity is H double prime AB. Okay. I just take all the artificial gravitational field to the corner by the choice of corners away. Whenever I calculate H double prime AB, if it's not a 0, I'm sure 100% that's due to gravitational. Yeah. Okay? Let's work off this one. So I'm going to make a first corner transformation. Double prime A equal X prime A plus epsilon. Now I use hat in order to distinguish this guy. Right? Plus all X all students. If I do this, you can see, but now I require I just use transformation to aegis burden is equal. Where actually, or delta hat equals 0. Double prime AB equal 5 prime AB minus 5 B
Farklı değil
minus.
Farklı değil
It's
galiba.
actually the same thing like that we did. Plus theta AB that has 6, right? Now you can see if I send it down just simply double prime A, B, I will rise A, then take a derivative of dA. So this actually will be 5 prime A, B, then A, minus rise actually, this will be, let's see, this A, B, take it, this will B, A, right? Why? Because let me write this again. Prime A, B equal 5 prime A, B minus 5 A, B. So I rise A, this will be B, A minus actually A, B, right? This actually the component with the derivative up, this actually the component up with the derivative down. Plus delta A, B, say C, right? This is mine. So now I take a derivative with respect, then sum derivative with A, this actually will A actually will give me right, this one. Now here minus psi A, B, A. So this actually, this is equal 0. This actually minus delta A, B, say C, A, correct? Now this A equal B. This is going to be plus, right? Here. Is that right? This we already know equals 0, right? This actually will be 0. No, this guy is so that's why I do call this here. Minus 0. Which means if I make a further coordinate transformation in double prime, I still have this one. I still have this one. Then my equations will be 1/2 x double prime let's see this actually 14. This is another point, you see the same, huh? But I have 2 gauge further. Say, you will see until this point I have normal gauge. Now this is purely gravitational wave. 5 prime AB still has a part due to current transmission, part due to the association. But now I take all the part due to the corner choice away. Now the edge prime AP is exactly the so this is exactly the next step. I'm going to show you using these two gate transformations. So gravitational wave we have only two components. Otherwise you cannot have down to two. Remember HAD we have 10 components. So how you can get it down narrow to two? You need to have 8 gate conditions. 4 from here, 4 from here. 4 plus 4 is 10 minus 8 equal to, I have only 2. Okay? Yeah. So we will do this next. Okay? Yeah.
Thank you. Start at 11:30 exam, right? And then afternoon there is one tutorial. And in afternoon we will have attendance as well as we will have feedback.